Hello, and welcome to the first video of our unit on vectors that we're studying from the Alonso and Finn text, Fundamental University Physics. If you don't have the textbook, it's not a big deal. There should be lecture notes that I'll be writing out in the description below, so click on that to follow along or just to have on hand for later. So, vector algebra is important in physics for a lot of reasons, mostly because it's a super convenient shorthand for a very more complicated conceptual framework. Just like regular algebra, 3x plus 2y equals 6, or even the diagram on the xy axis, just like these mean the same thing, and what they both mean is that they are shorthand for the set of all x's and y's that make this true. Vector algebra has a very convenient understanding of it being a shorthand so that it's useful for the modern physicist. So it becomes much more easily understood what vectors are, how to use them once the shorthand is understood, and that's what this unit is going to be about. The main difference between vector algebra and regular algebra that you learn in high school is just kind of a different interpretation of notation. Okay, so to begin with, we're going to start with understanding the concept of direction. So the way we get a concept of direction is we start with a straight line, say like that. It goes off forever in both directions. Now, on any straight line, it's possible to move from a given point in two different directions. So say this is our starting point. You could move in this direction, or you can move in this direction, right? So since there's only two directions and we need to talk about them in a way, we can assign a sign to each of those. We'll call this one positive and this one negative. And that has, now this has become an axis because we have a defined direction with the defined, a way to define direction in one, or movement in one direction or the other. So, so that's in one dimension. Direction in a plane, you have your axis, and so your starting point is here, but you want to move in this plane that is the surface of the whiteboard here. So say you move like this, right? So it's determined, it can direction in a plane can be determined by an angle from the reference axis. So you have to have a start out from an axis, and then the angle that is the displacement above or below the reference axis. And by convention, this is measured counterclockwise. It can be measured the other way around too. It often is. It depends on what you need, but in the general sense, we conventionally measure counterclockwise. So opposite directions. So say this versus this. Opposite directions, pretend these are parallel. They are determined by the angles, either theta and pi plus theta for radians, or theta and 180 degrees plus theta for degrees. Okay? So, because that will get you all the way back to this direction, like that. Okay, say we're not just talking about a plane, say we're talking about 3 space. So we have 3 possible directions to go, and we're to move in this direction here. And that actually comes out of the board a little bit. So say this is x, y, and z, right? So again, now we're going to need two angles with and two reference axes. So our first reference axis will be this one. So this is our angle because this is clockwise, counterclockwise. So this is theta. And then our second reference axis would be the z-axis, and we can measure an angle here, phi. So two angles to get the direction it is away from here in this plane, and then the direction it is away from the positive z-axis. Okay, so that's the basics of direction as a concept. Now we need to talk about, there's two different types of mathematical entities that we're going to be talking about: scalars and vectors. So a scalar is any quantity that is determined solely by its magnitude. So that can be things like volume, temperature, charge, things like that. Where a vector is a quantity that is not just a magnitude, but also requires or indicates a direction along with it. So that would be things like displacement, velocity, force. These things all are directed in some way, and that's why we represent them as vectors. So there's a graphical representation of vectors and a written representation of vectors. So the graphical representation is as a line segment with a direction, and the direction, it points in the direction that the vector is pointing, or the line segment points in the direction that the vector is pointing, and then the length of it is equal to the magnitude, is proportional to the magnitude of the vector. Oh my goodness, I can't write today. So, you know, if you have one vector that's 3 and another vector that points in the same direction that's 6, you have to write it or draw it as double the length. So that's the graphical representation of a vector. When writing a vector in text or textbooks, you'll usually see it as bold, like this. That's difficult to actually write on paper or a whiteboard. So we will typically write it like this with an arrow over the top of it. Okay? So that's how we denote a vector while writing. So like this is defined as the vector v. Okay? Let's see. So the variable that's assigned to a vector but without the arrow marked over it, so say for v we just have this. This is or not written in bold like the vector is written in text. This represents the directionless magnitude of the vector. So this would be equal to just the absolute value of the vectors, just the length of the vector, not without any direction attached to it anymore. Let's see. Now a concept that's very important is that of a unit vector. So a unit vector is a vector that is length 1. It's only 1 long, and so basically just indicates the direction that that you're talking about. These are often used to define the axes or the basis axes of a coordinate system or space. And they're typically written instead of with bold or an arrow, they typically are written with a hat over them like this. So U hat. or I hat, or UX hat, UY hat. The little caret or hat makes it be known that it's a unit vector instead of something else. Okay, so that is defined as the unit vector u. Handwriting on the board is terrible today, but I'm sure that will improve as I do these. So if you want to write any vector v in terms of the unit vector, then you can simply write it as the unit vector times the magnitude of the full vector. So this because the unit vector will point in that direction, assuming this is the vector that points in the same direction as you. An important thing is that the negative of a vector is the same as, it has the same magnitude but points in the opposite direction. So negative v, if this was v, then this is v negative. All right, next, if say we have two vectors, v and v prime, and let's say they're parallel. They may not be the same length. They don't have to be different, but we're going to say they're different. But they're parallel. Then v equals this, and v prime equals v prime, like this, right? So if we have a quantity, any quantity, say lambda, that is equal to v over v prime, then v equals lambda v prime, right? And we can see that. This is the multiplier, right? So v, if we sub this in, we have v equals v over v prime times v prime. Well, the magnitude of the v prime is going to fall out, and we're just going to have the magnitude of v times the unit vector of v prime, right? That cancels, and you're left with the unit vector in that direction times the magnitude of v, right? This only works because they're parallel. And so it works backwards too. If you have two vectors that are that have this relation where if you basically, again, if they have the relation where one can be multiplied directly into the other and it's equivalent, then they must have that relation like that, which must mean that they are parallel. Okay? There'll be different lengths, but they're parallel. And that's not super important right now, but it becomes very important later when linear algebra type things become more important. Now the big part of this whole topic, the big concept we're going to get to in this first video, addition of vectors. All right, so we're going to treat all of this by means of displacements, because displacements are vectors, but the rules for displacements will generalize to all vectors, even once you generalize to spaces bigger than makes sense to make displacements in, 10 space, 20, whatever, however many variables you have. The rules for vectors that you get from looking at displacements generalize out in a relatively simple way. So say we've got a 2 space here. This is x and y. And so this is motion from the origin here at the where the x and y axes cross to this point here. This is displacement. We're going to call it A. This is a displacement in space from here to there, right? So the way that vector addition works, you can understand from these displacements. Say you move from, let's just make a space here, move from A to B and then to C, which is here, okay? So you're moving from A to B, that's this displacement here, okay? We'll call that, and I need to make this bigger. Okay. Okay. Say we're in a space here and we're at point A, and then we move to point B, and then from point B we move to point C. Okay? That's 2 displacements, right? We're displaced from here to here. Call that vector AB. And then we displace from here to here. And we'll call that BC. Okay? So that's 2 displacements. Now the rule for understanding addition of vectors is that a displacement followed by another displacement is equivalent to the displacement from the first one to the end of the last one. Like that. So these 2 things are equivalent. And the way we write that out is AC equals AB plus BC. Okay, so we're adding these 2 vectors. When we add the vectors, we move from here to here and then from here to here. Let's see. It doesn't matter what order we do them in. We can move them around, whatever, if we have this vector and this vector. Okay? The way it works is if we're doing this displacement and this displacement, we have to take one of them and stick the tail to the head of the other one, so that this one will be first and this one will be second. So translate that down to here, and there's our resultant vector. Right? It doesn't matter what order we do them in. So let's show that with this diagram. So we've got this vector plus this vector, but we can do that one first and then this one second, and we get the same result here. Right? This plus this is this, this plus this is this. This is called the parallelogram rule, because you're making a parallelogram because these sides are equivalent to these sides. So this is an expression that vector addition is commutative. That means that you can do them in whatever order. It commutes. Just like regular addition. 2 plus 3 is 5 and 3 plus 2 is 5. Subtraction works the same way. If you're doing this and this, but you want to subtract this one from this one instead of adding. So this, we'll call this A and B, and you want to do A minus B. So what you need to do is remember that the vector B, the negative of it, is the same magnitude but in the opposite direction. So you're going instead to do A, B, right? And then you add. So we've flipped this around. This is negative B, and this is A, and now this is the resultant. Right? Now, the nitty-gritty of this is calculating the magnitudes and directions. So for that, we'll have to break out some trigonometry. But we've got two different pieces. We've got the magnitude, which we'll do first. So if we want to get the magnitude of V equals V1 plus V2, then we've got to look at this. So so we're going to say this is V1, and this is V2, and this is V. Okay? V is equal to V1 plus V2. I'm going to label some spots here. B, C, and D. And, you know, we might as well do this. E. So this is the altitude of the triangle. This is also a right angle here. So we can see from the diagram here, just based on the Pythagorean theorem, that V, the magnitude of V squared is equal to, so that's this length, is equal to this length, AD squared, plus this length squared, right? So what is AD? AD here is, what's AB plus BD, okay? AB is V1, and then BD we have to get from trigonometry. Okay, so let's define this angle theta here. And from trigonometry, from our rules, we got SOHCAHTOA, right? So the length of this side, BD, that is the adjacent to the angle. So we've got the cosine of theta equals the adjacent over the hypotenuse, BC. Well, BC is just V1. Or V2, I mean. And then we can pull that out over here, so we get the length BD equals V2 cosine of this angle here that V2 makes with the reference angle here. Basically the angle that it makes away from AB. So plugging that back in here, we've got V1 plus V2 cosine theta, which then we can plug back in up here. Equals V1 plus V2 cosine theta squared plus, now we need CD. Well, from the same thing, we've got that as the opposite over the hypotenuse, right? So that becomes V2 sine theta squared. Now we get to use a little bit of moving stuff around and a trigonometric identity. I'm going to erase this and recopy it. So we've got v squared equals v1 plus v2 cosine theta squared plus v2 sine theta squared. Okay? So if we multiply these both out, we'll get v1 squared plus v1 v2 cosine theta plus v2 squared cosine squared theta plus v2 squared sine squared theta. Right? Okay, so now let's do this. We were, out of this term and this term, we're going to factor out the v2 squared. v1 squared plus v1 v2 cosine theta plus v2 squared cosine squared theta plus sine squared theta. And this is a trigonometric identity. This equals 1. You can look that up. That's high school math. But that equals 1. So we're left with v1 squared plus v2 squared plus v1 v2 cosine theta equals v squared. So v, the actual length of the vector, is the square root of that. And that is how you get the magnitude of the vector from vector addition. This is called the law of cosines. Okay? Now the direction is a little bit easier, a little bit less trigonometry. Direction. There we go. Sometimes my arrows end up looking like U's, but it's fine. So to find, so we need to find, going back to our diagram here, we need to find this angle, which we're going to call alpha, okay? There we go. There's our whole diagram again. Hopefully it's visible to you guys. Let me know if you're having a hard time seeing any of my writing or diagrams. I'll make an effort to make it different. So again, from the figure, we can see that we know CD is equals V2 sine of theta. But it also, if we're looking at the whole big triangle, alpha has a relationship too. So CD equals V, that's AC, sine of alpha. Now since these are equal to each other, obviously, we can set these equal to each other. So V2 sine theta equals V sine alpha, right? And then we can divide each side by the sines, and so we'll divide this by sine theta, sine alpha, and this by sine alpha sine theta, boop and boop, and we get this relation, V2 over sine of alpha equals V over sine of theta. And similarly, because of BE being, so B down here at the bottom of this triangle to E here, that equals V1 here sine alpha, because this is a right angle, right? So we can still do these relations. This line is equal to this sine alpha, again, because of our SOHCAHTOA rule. But it also equals V2 sine of beta, which is this angle here, we'll say. Okay? It's just the same, it's just the other part of the triangle flipped around, right? So that gives us a similar rule, V2 over sine alpha equals V1 over sine beta. But we can combine them all together and know that V over sine theta equals V1 over sine beta equals V2 over sine alpha. This is called the law of sines. So law of cosines to get the magnitude, law of sines to get the direction. Now, sometimes the trigonometry can get confusing on this, and we'll look at that when we go into the problems on the next video for this unit. But that is basically the theory behind how it works. You have to be careful with what you mean by theta. The classic mathematical definition of law of sines just gives you a triangle, general triangle with angles A, B, C and sides A, B, C, and just tells you what is it? A over sine A equals B over sine B, lowercase b, equals C over sine lowercase c. And that works. It's just not the way it's presented in for addition of vectors, because sometimes you get this, and this is the angle that you have, and you have to just be careful with the angles when this one's acute versus obtuse. So that's this unit, this part of this unit. If you have any questions, leave comments. If you didn't understand something, need a clarification, again, leave comments. And the next video the next video in the physics unit will be problems covering this section.